Guitar pedals come in all different shapes and sizes. Here's a generic pedal that's about 5 by 7 inches. Next to that, let's compare a passive volume control pedal that's about 11 by 4 inches. It takes up a bit of space on the pedal board, doesn't it? Here's my new pedal, the Voluino. It's only 3.5 by 5 inches and can process guitars, basses, and keyboards. Let's take a closer look.
So what we have is a nice little device. It's at an angle. It's got some controls in the front. It's got an input and an output, and it's got a power jack, because this does have to be powered from anywhere between 9 and 12 volts DC, and it currently has 3 modes: an on-off mode, a normal mode, and a fast mode, and we'll go into that a little more later. The way it works, though, is completely different from other volume pedals. Instead of having a situation where you have gears or strings or anything like that, there are just 2 switches. As you press down, the volume up switch gets activated and the volume goes up. When you press the volume down switch, the volume goes down. It's as simple as that. It's a nice device, nice and small, easy to use, easy to modify, because it has an Arduino Nano inside, which can be reprogrammed. And it's relatively inexpensive. It's actually less expensive than most volume pedals on the market. So let's see how we can make a Voluino of your own.
Here are the various parts of the case. All of them, with the exception of the 2 sides and the 4 pivots, are 1/4 inch plywood. The actual dimensions are shown in these 2 drawings. Here's the case glued up from the 2 sides, front, back, and bottom. You'll notice that I drilled the 4 holes in the front before the glue up. That's because the 2 larger holes had to be countersunk on the rear of the front piece. Here's the top with the holes for the LEDs and 2 of the 4 pivots glued on. You can see that the LED holes have also been countersunk to let the LEDs peek through more. Here's the rear of the pedal with the remaining 2 pivots glued on. Again, all the spacing is dimensioned in the 2 drawings we previously saw. Here's the side view of the pivots, showing the holes that will accept the pivot pin. And here's the pedal's front. I'm going to assemble the circuit on a 400-point solderless breadboard. I'll temporarily place it on a metal plate, and when done, transfer it into the case.
We'll be using the X9C104 digital potentiometer module in this project. Let me just show you. It comes from Amazon like this. We have the chip here, a 10-pin header which you can break into 2 5-header sections, and on the back it has the indication of what each one of the pins are. Now I've already attached the header like this, as you can see. And the funny thing is that this does not actually measure between the header rows exactly increments of 1/10 of an inch. So you have to fudge this a little bit and adjust these. But they're all ready to go. Now the other device we'll be using is an Arduino Nano, just like that. Now we have other components we'll be using in the case, but on the solderless breadboard, as you can see here, we have 3 components. We have 2 1 microfarad electrolytic capacitors and 1 100k ohm resistor. We're going to start by putting in the Nano, and I'd like the first pin here to be in the first row of the Nano, and I want to leave 2 columns free on this side and 3 columns free on that side. So I'm going to push that in. Next I'm going to take the X9 C104 and position it so that C1 is on the left-hand upper side, and I'm going to leave 2 rows in between the Nano and the 109. Now we'll be installing a number of jumpers to make power and signal connections. Let's start with the power connections, and I'm going to refer to the wiring diagram. I'm going to start with the 5 volts. That's the 5 volt pin, and that's the 5 volt rail. Then I'm going to put in ground. Next I'm going to attach 5 volts to the X9 C104 right here. This is the pin in the upper left hand corner. Then I'm going to attach ground, that's right below the 5 volt connection, and I'm also going to attach the chip select pin, which is the bottom one on the left, also to ground. On the right hand side I'm going to attach this ground pin to the ground rail, and then I'm going to use a very small jumper to attach the low end of the variable resistor to ground. Next I'm going to attach these 2 rails together. I have 2 more jumpers to put in. One is going to go between D2 on the Nano to the up-down pin on the 104. Now I'm going to take another jumper and attach D3 to the increment pin, which is right above the up-down pin. I'm going to attach the 100K resistor next. I'm going to take a 1 microfarad capacitor, attach the positive side to the wiper, which is above the low pin, and to this 100K resistor. And finally, I'm going to take the remaining 1 microfarad capacitor and connect it to the row above the 104 and attach it to the R high pin. Now all the components that are supposed to go on the solderless breadboard are there. Now we will have to attach the off-board components that are in the case to the solderless breadboard.
Here's the solderless breadboard we just completed, and here are the components in the case. We have the output and input jacks. Here's the power connector that will bring in 9 to 12 volts DC. And finally we have the mode switch. And this will switch the Arduino between an on-off or instantly loud or muted mode, the normal mode, and a fast volume control response mode. Here you can see the label I printed and glued to the case front. And as you can see, I also painted the case a nice fire engine red color and put plastic feet on the bottom. I've connected the case components to the board also. Here's the input jack, the output jack, and the common ground from the switch, power connector, and the 2 audio jacks going to the rail on the board. Power goes to the Arduino's V-in pin, and plus 5 volts DC comes out of the Arduino and goes to the 5 volt DC rail. The wires from the switch for the modes are connected here, but we still have a few more components to connect. Those components are mounted on the case top. First we have the louder green and the softer red LEDs mounted on a section of prototype board. When I turn the top over, you can see the board also holds the 2 current limiting resistors, both of which are connected together to the black ground lead. It's easy enough to take the LEDs off the top since they are pressure fit into their countersunk holes. I have 3 wires coming off the board. the green LED green wire, the red LED red wire, and the common black ground. I also have the louder and softer switches mounted on some more sections of Pedalboard. I've mounted two number 440 by 1/2 inch screws on each board and secured them each with a 440 nut. These switches then mount to the top through the holes I drilled for them. I secure them to the top with two more 440 nuts per board. Now I have two additional screws coming through, and those are to secure two binder clips which will act like springs. I removed one handle from each clip and drilled a hole through the spring portion of the clip. I passed a screw through it and secured it to the top with a 440 screw and nut. Here's the pedal I painted black. I'll attach it to the top by passing a number 832 by 3 inch bolt through the four pivots. The binder clips act like springs, keeping the pedal in the center position, but allowing the pedal to rock forward and back, triggering the volume switches. With the top and pedal assembly done, we just need to attach the wires from the LEDs and switches to the solderless breadboard. I've connected the 7 wires from the top to the solderless breadboard. Let's go through them quickly. Here's the common ground from the LEDs. Here's the ground from the louder switch and the ground from the softer switch. Here's the softer switch lead going to pin D8 of the Nano. The louder switch lead goes to pin D7. The green LED lead goes to pin D4, and the red LED goes to pin D6. All that's left to do is to close the case up, attach the top to the case body, and reinstall the pedal. That's because I previously loaded the Voluino sketch to the Nano. Let's take a quick look at that sketch while I put everything together. The sketch starts by initializing the variables we'll be using. Then we begin the setup, where we define each of the pins and what they'll do. Then we light up both LEDs for half a second so we know the unit is on and working. The next instructions decrement the digital pot, bringing it to its lowest volume, so we always start with the unit's volume essentially off. We set delay up to 100, which is the normal mode. Now we go into the main loop. If the louder switch is pressed, we turn the green LED on and the red LED off. We set the flag FLG to +1 and increment the variable CNT. If CNT has reached its upper limit of 33, we set it back to 32 and then blink the green LED, letting us know we've reached maximum loudness. Otherwise, we'll increment the digital pot up 1 using the function aStep. In that function, if FLG is +1, we'll create a pulse whose duration is delay up long. We also use this function if FLG is -1, but using delay down as the timing element. Back in the loop, if the softer switch is pressed, we set FLG to -1 and decrement CNT by 1. If the count has gone below 0, we reset it to 0 and pulse the red LED, telling us we've reached the lowest volume. Otherwise, we'll decrement the digital pot by 1. During the times neither switch is pressed, we can poll the mode switch to see where it is currently set. If pin 10 is low, we set delay up to 10 for the fast mode. If pin 11 is low, we set delay up to 1 for the on-off mode. If neither of these pins is low, that means the mode switch is in its center or normal position, so we set delay up to 100. Let's end this walkthrough by looking at the sketch one more time.
I have input going here, output coming here, and I've set it into the normal mode. Now I have to power it. I can do it one of two ways. This first way is to use a standard wall wart and plug that in. This is a 12 volt. I can use anything from 9 to 12. Or I can just use a 9 volt battery like this. So this is just a 9 volt battery inside. It's got an on and off switch here. So let's plug this in. And then turn it on. And you noticed that the lights came on for half a second to let us know we're on. I have a keyboard attached here, which is in organ mode. You notice there's nothing there yet because it starts out as lowest. Let's go up. You notice it was solid until it got to maximum volume, and then it started blinking. Let's go down. Same thing. Now let's do the on-off. This is an interesting thing. I'm going to start playing the keyboard and press. So we can get a swell. So everything seems to be working. Let's try it out with the power cube. And plug this in now, and you'll see the lights go on again. There we go. We're still in the fast mode, so let's try it again. Fast mode. This is the on and off mode, and the normal mode. So everything's working well, and at this point I want to talk to you about how I put this one together to make it actually more rugged for on-the-road work. So for this project I bought these double-sided PCBs. So a whole gaggle of them, very inexpensive, plated through holes and pads on both sides. So this allowed me to create the supports for the switches and for the LEDs. But I figured since I'm going to use this in a situation where I'm going to be banging it around, rather than just keeping it on the solderless breadboard, I think I'll hardwire it in. And that's what I did. This is the hardwired version here. And as you can see, it's secured in with 3 440 screws and nuts from the bottom. And it's held up with a nut on under the board and a nut over the board to keep it in place so it can't move at all. So let me take this out and show you what the board itself looks like. And that's 3. These 3 holes are shown on the layout as far as dimensioning goes. Now what I did was, rather than put these devices directly in, I got some headed material and I put them in like that. So the headed material looks like this. This part can go on the board, and then you get this part, which you normally get with like the Arduino and everything else, and this plugs right in here. So you can solder this onto the Arduino or the digital pot, and then you can put this on the board, and then these devices can come out very easily. But they're nice and sturdy when they're inside. So this allows you to make the board without worrying about overheating components and the like. This is the back side of the board. And as you notice, for instance, let's take this wire, which is the 5 volts. It goes in and then it's soldered to the appropriate pin on the Arduino. And then it comes over here and it's soldered on the appropriate pin on the digital pot. So that's the way this thing goes. You notice I have a ground bus over here, and then I have all the wires connected. I took some extra wire and I twisted it around to keep the wires tight, and I found that this works really well in making a sturdy unit that can withstand the problems associated with musical gear being used on the road. So one final note, if you've gotten this far, I would really appreciate it if you give me a like. It really helps in these situations. I'd also like to let you know that if you would like to get a PDF that contains all the information in this video, plus some additional details that I didn't bother to put in here, you can email me at the address on the screen, and I'll be happy to send that to you. With that said, until the next time, see you then.